Hi everybody, Dr. Blum here. We're going to do, this is VSEPR part 3, and this is going to be on molecular models, and I'm going to call this molecular models COVID-19 edition. So let me just annotate this a little bit, because we're going to use things we have around the house to make molecular models to visualize those 5 basic geometries that we talked about. So those 5 basic geometries, electronic geometries to be more specific, and we're going to use pencil, paper, toothpicks. I made these little balls out of Play-Doh, but you can really do any kind of gummy candy or marshmallows or things you have lying around that you can stick the toothpicks in. And I'm also going to use some magnetic tiles that I borrowed from my kids to talk about these geometries. So the first geometry that we're going to look at is going to be the 2 electron group geometry. So let's 2 electron groups. Remember, an electron group is either a lone pair or an atom that is connected to a central atom. And the idea of VSEPR is these electron groups are going to get as far away from each other as possible. And so the electron geometry for 2 electron groups is linear. And we represent it on the page with the central atom and our 2 electron groups coming off of it. And it has a 180-degree angle. And so we can look at that in a couple ways. First, we can look at that just like a pencil, right? So it's just a line. We can visualize our central atom somewhere halfway in the pencil and our 2 electron groups. So that's our 180-degree angle. We can also take 2 toothpicks. You can see my 2 toothpicks. I'm going to use one of my Play-Doh balls as a central atom and then stick the other toothpick in. And then we'll use our external electron group here for our other 2 groups. What's nice about using the toothpicks is you really can see the idea of why these are as far away from each other as possible. Because really these electron groups, they can move around this central atom. This bond can kind of move. But the geometry that's obtained is when they are as far apart from each other as possible. And that is at the 180-degree angle. If this atom moves this way, or this atom moves over this way, that keeps them closer together than they want to be, and they want to be as far away from each other as possible. So you end up with that linear geometry with that 180-degree angle between the bonds. So here, I'll try to shake my hands out so you can see it. And that gives you linear. Our next geometry is going to look at 3, I have it way down there, 3 electron groups. And so with 3 electron groups, we get a geometry called trigonal planar, which again, I have my central atom, and I have 3 groups coming off my central atom, and it is a 180-degree angle. And so a couple ways we can look at this one. First, the easiest way to visualize trigonal planar is just draw the triangle on a piece of paper, right? So I can draw this triangle out on a piece of paper. It lives in a plane, right? So it's not very three-dimensional. And that is our trigonal planar. We can also look at it with our little toothpicks. And now instead of 2 groups, I can take my linear, and I have a 3rd group here. I have a 3rd toothpick coming along. And now I have 3 groups, and they are moving around this central atom, and their goal is to try to get as far away from each other as possible. And this geometry ends up, even with all 3D space available to us, it ends up as a planar triangle with 120-degree angle between the bonds. And so again, you can see that this should lie kind of on a straight plane, like a triangle. And then lastly, the magnetile, we can look at it, here's the actual like triangle, and again, it gets its name because we're at the corners of this equilateral triangle, and we can visualize this as my central atom right here in the middle. And again, we have our three planes, and again, you can see where it gets the name, trigonoplanar. So that is 3 electron groups. All right, on to 4 electron groups. So for 4 electron groups, the geometry that we get is tetrahedral. And what this looks like is I have a central atom, one kind of coming up, 2 coming forward. I'm drawing the wedges to say it's coming out of the plane. And then 1 going back. So those are my four groups. And of all the geometries, this one may be the hardest one to visualize. So let's get our toothpicks again. So we've looked at the 3. This was my trigonoplanar. Now if I have a 4th electron group come along, you may think this might go into a square. Run away, Bond. Run away, Bond. You may think it might look like a square. We often draw this like a square. If you're drawing methane, you often see it drawn like this. But that doesn't mean that's what it goes into three-dimensionally. Because in 3D, these can actually get further away from each other. And they form kind of this squatty-looking pyramid with a bond coming out the top. And so you can see how this representation, I have the 2 kind of coming out towards you here, and the 1 coming back, and then the 1 going straight up in the plane. If I draw my plane kind of where this is, I'll put a piece of kind of white paper behind it so you can see how they have the 1 coming up and the 2 going backwards, 1 going backwards. Now, my little Play-Doh model isn't perfect in terms of the bond angle, but the bond angle on this guy, instead of 90, which is what it would be if it was a planar square, this bond angle between these things is 109 degrees. Where it gets its name from, the tetrahedron, is if I'm taking these magnetic building tiles here, it's a triangle base, again an equilateral triangle, and we're going to make a pyramid out of it. So you can see it's a pyramid with a triangle base, and you can visualize the central atom is in the middle of this thing, and the external electron groups point to the corners of this pyramid. And this is called a tetrahedral or a tetrahedron because it has 4 sides, 1, 2, 3 going around and 1 on the bottom. So that's where we get the name tetrahedron from. And again, we can build this model with either the ball and stick. Just remember that it's not a square, and I kind of think it looks a bit like a spaceship, if you ask me, or a little spaceship guy who landed down Mars rover or something of that nature. And so his angle, I'll put it on my screen as well. This angle is 109.5 degrees. All the way around between all 4 of the different bonds. All right, now we're on 5 electron groups. So for 5 electron groups, we have a geometry known as trigonal bipyramidal. And what this looks like, you kind of have what we call the axial, kind of a stick coming up and down, and an equilateral triangle, 2 pieces of it coming out towards you, 1 piece going back into the board, coming around the middle of this thing. The angle between the up and the down and the plane is 90 degrees. And then around the triangle is back to that 120 degrees like in trigonal planar. And I'm going to give my little toothpick models a break here for a second. And I like to really use pencil and paper to make this model. So I'll go back to that paper trigonal planar that we had drawn. And I'll stick a pencil through it. And so you can see I have a pencil, part of the pencil coming out the top, part of the pencil coming out the bottom. And so you can really easily see the 90-degree angle that the pencil makes with the paper. And these are my 5 groups. I have 1, 2, 1 at the top, 1 at the bottom here. And then I have my 3 groups around the middle that make the trigonal planar part of this. And so going around the middle, I have that 120 angle. Take my Sharpie and mark that angle on there. So that's 120. So 120 going around the middle and then from top to bottom. And you can really see how it gets its name. We have unique names for these groups. The ones going up and down, we call them axial. So you can think about them pointing to the poles. And then the ones going around the middle that make the triangular piece are equatorial because they're on the plane, and you can think of that as like the equator going around the middle of the molecule. So these are equatorial here, and these are axial. I like that version of the molecule, and everybody has pencil and paper floating around, so you can make that and visualize that model. Where the trigonal bipyramidal gets its name, and so we can look back at that tetrahedron. Remember that was a triangular base. Looks like a little triangular pyramid. If I put a bottom to that pyramid, take 3 more tiles, and I build this kind of diamond-y looking shape. This is the trigonal bipyramidal. It's a bipyramid because it's got kind of that trigonal pyramidal on the bottom and on the bottom and the top of this structure. So that's where it gets its name. It's like 2 pyramids stacked one on top of each other. So it's a nice way to visualize it as well. The electron groups, we have 1 here, 1 at the top, 1 at the bottom, and then the 3 going around to the points in the middle of that planar triangle, in the middle of it. Moving on, last but not least, to 6 electron groups. 6 electron groups has a special name known as an octahedral. And very similar to trigonal bipyramidal, I have the up and the down, and then I have 2 going back and 2 coming forward here. And this is basically a square instead of a triangle going around the middle, and I have that up and down portion. And the angles on this are all 90 degrees all the way around. And I like to think of this, if you have a jacks, if you ever play jacks floating around, this looks exactly like a jacks. So I have, you can see that square in the middle going around, and the one coming out the top and one coming out the bottom. And we can also make this with the paper version. Here's my, again, I'm drawing that cross or square. If you can visualize connecting the points to this, you would get a square. Sticking my pencil through the middle. And so again, I have on the top and the bottom. And you can see pretty easily, again, the pencil to the paper makes that 90-degree angle. And then going around, I also have the 90-degree angle. Again, the gumdrop / Play-Doh models get a little cumbersome when it comes to this. It's just as easy to visualize with the paper. And lastly, we can look at the external model. So we can get our magnetic tiles again. And instead of picking a triangular base to build this, I'm going to use a square base. And so I'm going to have 4 pieces, and so I'm going to make one pyramid here. This is a square base pyramid. And then I'm going to take another 4 of the equilateral triangles, build it on top. Hopefully it won't fall apart on me as I do this. So I have, it's very similar, right, to the trigonal bipyramidal, but the only difference is I have a square around the middle. And this has a unique name to it. It's not square bipyramidal. It is called an octahedron, and it gets its name because it has 8 sides, 1, 2, 3, 4 on the top, and then another 4 on the bottom of this thing. And it looks like a nice diamond shape in 3 dimensions. All right, so I hope this helped you visualize these basic electronic geometries, and this is something that you can keep in your mind as you do this, and not just try to memorize this as a list of names and facts, and you can really visualize it, because when you visualize this, this is going to help you a lot as you do these problems, instead of just memorizing them with kind of weird names. They are very descriptive names that describe these geometries in nice detail. All right, thank you for joining me, and we'll see you soon.